Okay, so this is kind of well, let's see how far we got. So first thing, inscribed angle. An inscribed angle is an angle inside of a circle. Once again, we have a circle with a radius, but this time the vertex is a point on the circle. It's whose vertex is a point on the circle. So we have a circle here. This is an inscribed angle. So ABC, angle ABC is inscribed inside circle, let's call it O. We say that the measurement of angle ABC is equal to 1/2 the measurement of arc AC. We're not going to prove that. Maybe you could prove it. A couple of things. The inscribed angle is half. So the inscribed. So here's a question they give you. So they give you, here's a circle. They say here's the inscribed angle. They say, for example, question number 1, the measurement of angle ABC is equal to 40 degrees. Find arc AB. And you say, it's 80. 2, if the measurement of arc AC is 150 degrees, find angle ABC. And you say, that's easy because we just learned that the angle is half the arc. It's a 10, so it's 75. Another cute little question is, another fun question you might see is if angle AOC is equal to 60 degrees, find angle ABC. And you look, you say, well, that's weird. But then you realize that, AOC is a central angle. If the central angle is 60, the intersected arc is 60, and therefore the inscribed angle is half of that, so it's 30. Fun little things. And, maybe that might help you figure out the relationship between, the inscribed and, the arc. We're not going to talk about that. Let's see. Couple of things. Couple of fun little fun facts. 2 angles. So let's see. Fun facts. First of all, 2 angles. Can you see up there? Yeah. 2 angles. 2 inscribed angles. 2 inscribed angles that intersect the same arc are congruent. So if we look at this picture, here's arc AB. Okay? And then the first angle, let's do, ACB. And then if I put another angle in here, like, ADB, we would say that because, this is half of AB and this is half of AB, we can then say that these 2 angles are congruent. Kind of interesting. If you look at the picture, you're like, oh, you know what, that might have a use somewhere along the line. Number 2, an angle inscribed in a semicircle is a right angle. This is so awesome. Like, this is like the coolest thing. Oh, I don't want green, I want black. An angle inscribed in a semicircle is a right angle. This is awesome. Take a circle, draw in a diameter. And any angle you inscribe in there is a right angle. Like anything, like da, da, that's a right angle. Da, da, that's a right angle. Any color, it's awesome. It really is. Like da, da, that's a right angle. That's that's like major. And then you can kind of see, we can actually connect this because that was that whole unit. This is how they were able to create all these two relationships. That's what the Greeks were doing. They didn't have the numbers we have. That was later. They only had like Roman numerals. They didn't have 1, 2. They didn't have this. They weren't even using like numbers. And if you think about it, like we could create we could have done this whole course without mentioning like Arabic numerals once. So once again, they were, with all these interesting things they were discovering, they were able to create relationships and ratios, and this segment is equal to that segment. It's kind of awesome. Let's see, number 3, the opposite side of a quadrilateral inscribed, the opposite angles of a quadrilateral inscribed in a circle are supplementary. What does that mean? Well, let's get a quadrilateral inscribed in a circle. Let's think about this. So we have a circle. We have any quadrilateral inscribed in there. The claim is that angle A plus angle B equals what? Equals 180 degrees. That's the claim. Once again, inscribe a any quadrilateral in the circle, and the opposite sides are supplementary. I mean, let's think, or those two angles make up a straight line. How can we prove that? How can we prove that? That's number 3. So, Number 3, how can we possibly prove that? The opposite angles in a quadrilateral inscribed in a circle equal 180. How can we prove that? Well, it's kind of easy if you think about it. A and B are both inscribed angle. Let's draw in, is that a radius? Is that a diameter? I don't know. It doesn't need to be. All I know is that this A is 1/2 whatever this arc is. So let's call the red arc theta, right? What's left over for the remaining arc? Well, the remaining arc is the arc subtended by angle B. Now we know a circle is 360 degrees, so this part is 360 minus theta. Well, what is A plus B? Well, we know that A is equal to 1/2 of theta, and we know that B is equal to 1/2 of the remaining part of the circle. Let's add these together. Theta over 2 plus 360 over 2 plus theta over 2, equals 180 degrees. There you go. That's our proof. Once again, A inscribes part of the circle, B inscribes whatever's left over. The sum of the angles is 360. So if this is a dummy variable theta, this is 360 minus theta. We know the inscribed angles are 1/2 of it, added together, and we got 180. Nice. Now, let's do some interesting things. Now, let's move on. And obviously, the algebra questions, they follow through. Let's move on. Next. These next couple of exercises, I'm going to prove because it's interesting. Let's see. First one, chord tangent. So first we're going to find angles. Chord tangent. So if you have I'm just going to talk this through. If you have a circle and you have a tangent, right? No matter where you draw a chord, you can draw it in anywhere you want, like this. So let's say we have A, B, C. We have tangent segment. I don't think I used that word before. This is a tangent. This is a tangent segment. It's a tangent. So AB is a tangent segment, and BC is any chord. Angle ABC is equal to 1/2 the measurement of arc BC. That's kind of cool. Can we prove that? Yeah. Once again, we have all of our knowledge. So you know what I'm going to do? I'm going to let's see. I'm going to draw in a radius. So let's call the circle O. So OB is a radius. That means that OB is perpendicular to BA. I'm going to draw another radius. Let's say. So let's call this angle. Let's call this X. That means BC is X. Okay. Now, because it's a radius and this is a tangent, I know this is 90 degrees, right? Let's fill this in. I know that, let's call this 1 and 2. I know that 1 plus 2 plus X equals 180 degrees. And I know that 1 plus 2 equals 180 minus X. But because it's an isosceles triangle, 1 is equal to 90 minus X over 2. But this is a right angle. That means this angle ABC, is equal to 90 minus that 90 minus X over 2, which equals X over 2. That's our proof. That if you take a tangent and a chord, it's equal to 1/2 the intercepted arc. Cool. And then all the algebra questions that follow. Next. What's next? Chord and chord. This is kind of cool. You'll like this next one. Ready? Take a circle. So once again, chord, chord. Okay. I have any chord, right? The claim is that this angle here is equal to the mean of these intercepted arcs. The claim is that the measurement of angle 1 is equal to arc AB, the measurement arc, plus the measurement of arc CD divided by 2. That's crazy, but this is what they figured out. Once again, just draw any two chords in a circle, and the average of the intersecting arcs is equal to that angle in there. How do we prove that? Well, it's kind of easy. Just draw in, it's kind of easy, draw in this line right here. Draw in that line there. Draw AD. Okay. So you're like, wow, what big deal? Well, if you think about it, when we just drew an AD, we created two inscribed angles. So this is CD over 2. And this angle here is an inscribed angle. This is AB over 2. And this is kind of cool because 1 is the exterior angle. Once again, angle 1 is the exterior angle, and that's equal to arc AB plus arc CD, and they're both over 2. Once again, remember this from the beginning of the year. This is the exterior angle is equal to the sum of the two remote interiors. It's kind of cool. So you can see the algebra problems. It's in the book. I just want to get through this quickly. And so you can plug in the numbers, and they make you find the angles. That's basically, but this is the geometric proof of that. And we don't even need numbers. We can just show these relationships exist. Next. What are we? Secant. So you have a circle here. We have a secant and a secant. Okay, and we have A, B, C, D, and E, and the claim is, let's call, so for the next couple of circles, we're going to call the small one the red, and I'm going to call the big one the green. We'll call the big one the green. And the claim is, you're going to like this one, this is kind of interesting, that angle C is equal to 1/2 AE minus BD. The big arc minus the small arc divided by 2, that's this angle up here. How do we get that one? Let's think about this for a second. Well, I'm going to ask you to draw, like over there, I'm going to ask you to draw it. How do we prove this? Once again, we don't have numbers. This is like 2,500 years ago. How did they prove this? Well, I'm going to ask you to draw in a line BE. Here's the proof. Construct BE. Well, what have we done? Well, we've just created 2 inscribed angles. Does this here, let me get my red pen, sorry. Over here, this angle here, this is 1/2 BD. And right here, this is let me use my green, this is 1/2 AE. Well, it's the same exact thing we just did in the last unit. Once again, this is the exterior angle to the 2 interiors. So we have 1/2 AE, the green, is equal to the red plus angle C, manipulated it around a little bit, and we see that we subtract this over and we got our formula. Angle C is equal to, I'm going to use the colors. We have 1/2 AE minus, sorry. 1/2 AE minus 1/2 BD. 1/2 BD. And there's secant, same idea. So I'm just going to put the formulas up for the other 2. The other 2 combinations are secant, tangent, and tangent. Tangent, it's the same idea. So let's just do secant, tangent. So you have a circle, you have a secant and a tangent segments. Same idea, you have a green and a red. And let's call that, what is that, angle C. And the idea is angle C is equal to like 1/2 the green minus, 1/2 the red. And it works the same time. I don't even write it the other one. Same idea. If you have tangent, so if you have a circle here and you have, the question is, what is it turns out, it's the same formula. Here's the green, here's the red. Strictly out of the book, it's the same formula. And here's angle C. So once again, these both use this formula. Same idea. There's going to be like a small and a large. Small, large, you subtract 1/2 Yeah, so like 1/2 the green minus 1/2 the red, or you subtract the difference and you take half of it. These are the formulas that, this one's, it's not as difficult. If you think about it, if this is theta, if this is 360 theta, then we have angle C is equal to 1/2 360 minus theta, you get 180 minus theta. And so you got this weird, as long as you know the red, the red and this angle are supplementary to each other. But you can always stick with the formulas you get. Let's move on to the last part. Let's take a look at segment lengths. No, let's stop this video.